Hi everyone, welcome back. I'm Richard. This is Very Little Evolutionary Game Theory. We're in the third lecture, and we've done evolution of conflict, evolution of cooperation, and today I want to do evolution of relationships. And what I mean by that is just the most vestigial applied mathematics version of a relationship, which means there are individuals who interact with one another multiple times, and they are capable of remembering that. Yeah, and that makes it, that's our minimal definition of a relationship. It may not be a satisfying one, but it is the one we will use in this lecture. When you add relationships to basic game theoretic models, lots of things can change. You have to also add strategies that can make use of the repeat interaction, but when you do, the games become very complex in lots of interesting ways. So I'm not going to, in an hour and a half, give you a full tour of all of the fun things that can happen in what is called repeat game theory. But I do want to give you an accurate look inside the basic mechanics of how we set up models with repeat interaction, what it would mean to have a strategy that makes use of repeat information, and then some perspective on the kinds of evolutionary dynamics that occur in games like this, so you don't hastily generalize particular results from certain models. To set this up, I want to use a new version. Well, first let's talk a little bit about biology. I'm getting ahead of myself. Why do we need to do this? Well, if you're interested in people like me and many of my close colleagues, it's obvious, hopefully, that you want to model repeat interaction because your interactions in your daily life are mainly not with strangers, right? I mean, the people in the room around you are sort of strangers. Yeah, but you know them, right? You're having repeat interactions. Yeah, or with your friends or your romantic partners or your children or whatever it is, your parents. These are repeat interactions, and there are many possible strategies open to you where you can use past information about how you've behaved and the other individual has behaved to choose how you behave with them in the future. Other animals are similar. Not all animals are asocial or antisocial. Yeah, even cats have social lives, right? The cat owners here. Cats have rich social lives, remember their owners, know their names. They know their names, they just don't care, right? That's what we say about it. But they're not asocial. Many animals and plants are social. They have repeat interactions. And if evolution can design strategies which make use of information from repeat interactions, the idea goes, then it will favor certain strategies that are contingent, that is, decide how to behave towards an individual based upon how that individual has treated them in the past. And we want to make that into something formal instead of just hand-wavy moralizing. Yeah, and so that's the point of repeat game theory, is to explore those intuitions and implications. But I mean, you think about it like, you know, the tropics are basically just a habitat for termites, right? Okay, so termites have repeat interactions. Yeah, this is not one-shot stuff. A termite society is a civilization, so to speak, and with lots of overlapping generations, complex social structures and interactions. If we have any hope of understanding these things, we should start out by figuring out what natural selection would do if it had its way in contexts where individuals meet one another repeatedly and can remember individual identities and how they treated them in the past. I don't know if termites do that. I don't know if they remember the identities of other individual termites, but there are lots of animal societies like that where individuals can interact repeatedly over time. Okay, with that biological justification, I hope you find it plausible that this is a big deal empirical context to model repeat interaction. Instead of reusing the games from the previous lectures, I want to introduce a new payoff matrix. With some apology, because I know you've got enough already, and I could reuse the previous ones, but the math is going to be easier if I use a standard formulation for a cooperation dilemma instead of the ones I used previously. So I want you to, again, think about a two-player game. Two individuals, they can have different strategies, and this is going to be a cooperative context in which both individuals have the opportunity at some personal cost to provide a resource to the other individual. And when they do that, said that their behavior is cooperative. So we're going to have just two strategies to start, cooperators and non-cooperators. If both individuals cooperate with one another, then row player gets B minus C, where B is greater than C. And again, these are in marginal fitness units, changes in fitness. So the aid you receive, that B is coming from the other individual, the C is coming from yourself. Yeah, so your net benefit is B minus C. The other individual is also getting B minus C because they also cooperated. Yeah, and you generated their B and they generated their C. Does this make sense? So there's a private cost, perfectly private cost, and a benefit that is generated by the other individual, but you don't generate any benefit for yourself. So this is a kind of classic, simplified mutual aid situation. There are also non-cooperators. I'm going to write non-cooperator to, hopefully that's a label free of judgment, right? So this is evolutionary biology. We don't moralize, at least not in the beginning, right? We're not judging the non-cooperative strategy. They're just doing nothing, right? It's those bossy cooperators that come in and want everybody to cooperate. What's up with that, right? The non-cooperators are minding their own business. If you're a cooperator and you get paired, you're a cooperator, you get paired with a non-cooperator, you provide aid, but they don't, and so you get minus C. Does it make sense? Yeah, you can picture this, right? Think about your housemates again. Not to start any fights, but yeah. Living with people is hell, isn't it? And then we've got non-cooperators here. Flip side of this interaction, non-cooperator paired with a cooperator. You receive aid B, but you don't help, so you just get the B. Again, the non-cooperator in this model is just kind of inert, right? They're just doing nothing, yeah? The cooperator does something at a personal cost, which benefits the other individual. Non-cooperator, non-cooperator, then we get our 0, right? Nothing changes. This is what defines non-cooperation as inaction in this model. We're just imagining that it's doing nothing. Yeah, cooperating is like taking your friend to the airport, whatever that is for, small mammals. I don't know. but yeah, the other individual gets the benefit and you pay the cost. That's the idea of the structure. Before we proceed and analyze this model, this is the classic so-called additive prisoner's dilemma. And the issue about it being additive is something I'll postpone explaining until the next lecture on Monday, where it will be, is it on Monday? Yeah, where it will be important to talk about what that means. Right now, it's just to say that it means there's no synergies. So if both of you help one another at the same time, you could have a model where that's synergistic, and you actually get more benefit from that. Yeah, that would be a different kind of cooperation model. The cooperation here is sort of asocial. What the other individual does not influence the benefit they receive. I'll say that again. What the other individual does not influence the benefit they receive. Right? There's no joint benefit to cooperation in this model. It's like the check is in the mail. You both write checks to one another or something like that. Yeah. Does that make sense? So it's this asocial model. It is not in any sense general or universal, but it's easy to analyze, and so it's really common in the biological literature to analyze this model. But this model is actually quite pessimistic about cooperation because there's no synergies. If you put synergies in it, it's easier to get cooperation to evolve. So I just want you to keep that in mind as we analyze it. You're going to learn a lot about the qualitative structure of games like this, but the quantitative details do depend upon the details of the payoff matrix, if you add synergies and things like that. Yeah, Christine, do you have a question?
If your own cooperation would also give benefit back to you, then it could easily be transferred into coordination, right?
That
it
it's
depends on the benefit cost ratio?
Yes, it depends, and I want to stick inside the prisoner's dilemma so that I can focus on the core area of the literature. But all of this repeat stuff is interesting in coordination games too, I think, and all of those sorts of games matter. Hawk-dove, you get to a hawk-dove structure, repeat play matters a lot there too, right? Because you want to find some way to keep playing dove and not break down and think about doing the dishes, is what I call it in my book, that doing the dishes in a housemate situation is like a hawk-dove game. You both want clean dishes, but you'd rather the other individual wash them. Yeah, let's be honest. Yeah, but you get a machine, right? But then it just breaks down into who loads it, right? So it's an infinite regress, right? Just throw all the dishes away and buy them new every week, something like that, right? That's the solution. And dishes are cheap at IKEA, right? You could in principle do it. But yeah, to Christine's question, the easiest change is, yeah, you produce some common good, and so you get a share of your benefit back. That changes the definition of C, is the way to think about that, is it reduces your cost, because your net cost is going to be smaller if you get some return from the general good you produce. So this version is nice cognitively, because the B's and C's are in a sense pure, right? And you can just read off the payoff matrix what the consequences are. It gets, as you add more realism and spillover effects, it just gets harder to process.
That's not so surprisingly that you can transfer one game to another according to the cost-benefit ratios, but in terms of, this shows so clearly that your research goes in a direction how you really put assumptions in, right?
Yeah.
I mean, yeah.
Yeah.
You need really good, realistic ideas behind it.
Yeah, absolutely. Yeah, and anyway, there's lots to say here, but I'm going to control myself, and maybe we'll pick up this thread again on the next lecture. I need to make some progress here on this. Are there questions about this game? No? It's a prisoner's dilemma. Let's just analyze it with our eyes before I start writing algebra down. Prisoner's dilemma, so remember what that means. That means no matter what your opponent does, or your partner, we don't have to call them your opponent. It sounds menacing. Your partner does, natural selection would favor not cooperating. So we can just put ourselves in each column and ask about switching rows, because you're a row player, right? So imagine you knew that your partner was going to cooperate. You would do better by not cooperating, because B is greater than B minus C. Yeah? Likewise, if you knew your partner was not going to cooperate, you do better by not cooperating, because 0 is better than minus C. You see that? So, wah wah, sad trombone noise. Yeah, that was my sad trombone noise. Wah wah, that was better. Okay, I'll practice for next time. Make sense? Okay, so you just did game theory with your eyes. Congratulations. It's that, with simple games, it's that easy. You can just analyze the 2x2 matrix. As you add more strategies, this gets harder. Yeah, and then we like to do the math and make sure we understand what we're doing. All right, so you know what's going to happen here. The only ESS is not cooperate. Yeah. Cooperate can always be invaded, right? Because when it's common, it's getting B minus C, but the first non-cooperator gets B, so non-cooperation invades. If non-cooperation is common, everybody's getting 0, but the first cooperator gets minus C, so they can't invade. Bad times. Yeah? Okay, so that's the dilemma. When we add repeat interaction to a model like this, what we imagine is that individuals are still paired together and they play this game, but they do it multiple times. Each time they play it, there's some probability the relationship continues. And I'm going to invent a new symbol, little w, which is the probability the relationship continues for one more time. But every time you play the game, there's a chance it continues. And so think of W is like the probability on a biased coin. If it comes up heads, then you continue the relationship. Yeah, so this is just a statistical mask for whatever the biological processes are. that have to do with the continuation of relationships, which will be some mix of your lifespan, yeah, and also your cognition and other things that aren't contingent upon play in the game, right? So they might just give up at some point and someone walks away, or they might, expire.
Why W is the same as the payoff? No, the fitness.
Well, this is little w, and I don't know the reason. It's just if you, I think that one of the classic papers, I think Hamilton used W in one of the first papers on this topic, and so that's why I adopted it. I forget. But usually with these models, I'm teaching for the primary literature, right? And so I pick up the symbols from the papers, but I don't remember in this case where it was. So it's a real shame that the Roman alphabet has so few symbols, and we end up like, they just collide all the time, right? And then, I'm always tempted to use Greek, but this has tragic results with many audiences, right? Once you get beyond alpha and beta, like people have, it's just squiggles to people, right? And it's just horrible. I did 2 years of Greek in college, so I'm very comfortable with the Greek alphabet, but most people I've discovered are not. It's just like squiggle 1, squiggle 2, squiggle 3, right? So it's no use. I should use Cyrillic. Yeah, I think Slavic speakers would like this, right? But that would be even more disruptive to education, probably. Now we have backwards R. Yeah, lots of possibilities there. My mind is abuzz with the possibilities. Okay, I'll suppress that. But little w, the probability relationship continues another time. So let's think about how to calculate payoffs in a scenario like that. And I want to gradually build you up over the next, say, half hour to 40 minutes into analyzing repeat play in the basic additive prisoner's dilemma. And as we do that, we're going to start by just analyzing these non-contingent strategies that make no notice of the fact that they're in a repeat game and show you that it changes nothing in that case. But then we introduce a strategy that has contingent play, pays attention to what happened in the past, that can change things quite a lot. That's the goal. Okay, so let's start by thinking about the payoff to cooperators in repeat play. Two cooperators meet. We can diagram out what happens. We've got two cooperators, and they interact over a series of, let's call it rounds, turns, the number of times they play the game. So the first time they meet, they're paired up through some random process that we're not modeling, right? There's no assortment here yet. We're going to have repeat play though, and I want to show you that it's kind of a form of assortment. But there's no assortment in pair formation. It's just completely random with respect to your strategies. So it turns out this pair is two cooperators, so they both cooperate on the first go. So that means focal individual gets B minus C, yeah? And then the next time there's a chance W, they continue to the second turn. So let's assume that happens, and they're gonna cooperate again because that's all they do. Yeah, they just cooperate. And then you get B minus C again, and again, and again, and again, and so on, potentially forever, right? So if you're really lucky with your coin flips, some particular pair, if you imagine an infinite, this is the thing mathematicians will say, imagine an infinite number of pairs. It is, with probability one of those pairs will continue for infinity, right? This is the kind of nonsense mathematicians say. Yeah, we need to calculate out, other pairs though are only gonna have one interaction because their coin flip, W, is going to come up tails on the very first time, and they're not going to interact a second time. Most pairs, well, it depends upon what W is, but under reasonable ranges of W, most pairs are going to have some intermediate number of interactions. Right? There will be a distribution across a bunch of pairs of individuals of how long their relationships continue, and that will be determined by W. Right? And that will affect the average fitness benefit of interacting in this game for cooperators. Does that make sense? We're going to do that calculation now, but I want to prep you for why we're doing it. It's the idea that you can't just say B minus C. You need to know how many B minus Cs you get, and that's a distribution. Because some pairs interact once, some interact twice, some interact 3 times, and we can write down the probabilities that happens because it's determined entirely by W. You with me? This is the intuitive talk through first, and then I'm going to start writing equations. But I want to pull those two things apart. Christine.
Yeah, also, yeah, you made clear before you want to talk about the prisoner's dilemma, but if you would be in an ideal population of all cooperators all the time with this kind of payoff matrix, actually would have the same benefit as if you would be a single individual, right? Not in a cooperative group, because you would have a benefit minus costs, like you act for yourself, and like you are not a social species, you know? It's with this payoff matrix, it's actually the same outcome. I mean, if you would be in a, if it's not frequency dependent, and you would be in a population of just cooperators. So conceptually something different, but mathematically it would be absolutely the same, isn't it?
I'm not sure. Let me push through, and then you can try to convince me of your point again later.
When other individuals, other strategies come in,
then everything changes. Yeah.
If you would be just among cooperators, then
yes.
Then cooperation would not have an extra benefit over acting just by yourself. What? I don't know. It's, I mean,
well, I think I see where you're going. Let me push forward, and then you can insert yourself again at the point where you think it is most effective to make your point.
Yes.
Because I think I'm driving to the same issue, is that the basic issue we're going to reveal about cooperative play is, I mean, not cooperative play, repeat play, is that you'll get a bunch of strategies that behave the same as one another, even though they're different strategies cognitively. All right, so and this is one of the first things we're going to discover about these games, and that has a huge effect on how we're supposed to make predictions from these games. Actually, it's terrible, but it's reality. So lots of strategies will produce the same behavior in the presence of one another. Yeah, and that's the cooperative strategies. Could be cognitively different, but have very different consequences. And that doesn't matter until you introduce defectors. And they behave differently towards defectors, and that's what determines the evolutionary dynamics. So the evolutionary dynamics are driven by these rare interactions in these games, not by common ones. And it's a very,
yeah, I know.
And I know you know this, yeah.
It's just, I'm so sorry, I just so feel, I find it's realistically strange that there's no benefit of cooperation. As not a higher mutual benefit of corporations.
Okay, let's write down a payoff. So I did my hand waving about W's and the chance you interact 2 times, 3 times. Let's actually do it now and actually write this down. And there's 2 ways I want to derive this payoff for you. And they're both legitimate and they're both in the notes. But I think they each have benefit, so just indulge me doing the same derivation twice. Is that okay? It won't offend you? So we're going to try to write the payoff, the expected payoff to a cooperator who interacts with a cooperator. Okay? And by cooperator here we mean they always cooperate. So maybe I should write it like, well, what do I do in the notes? In a moment I change this. So let's invent a strategy that's called all C, which is all cooperate. All they do is cooperate. So this is just to distinguish the strategy in the repeat game from the behavior in the one-shot game. Right? So there's a cooperative behavior, but the strategy in the repeat game we want to talk about is all C, meaning they always cooperate, no matter what happens in the past, no matter how long they've been in the relationship, no matter what their partner did to them in the past, they're always going to cooperate. Okay? This is your ideal housemate. Yes? Okay. This animal might have memory, but it's not using it under all C. Right? We can't judge if they have memory or not, but they're not using it. That's what we know. Okay, so this is like writing other payoffs. We just start with the consequences, what happens to you. So you, all C meets all C. First turn, they both cooperate, so you get B minus C. And then there's a chance you interact again. And that chance is W. And then what happens? Well, if you interact a second time, you also both cooperate. And so you get B minus C again. But we're not done. Oh no, this expression is infinitely long. It's my favorite kind of expression. Yeah? I mean, why settle for a finite expression when you can have an infinite one, right? So now there's a chance W squared that you interact 3 times. Are you with me? The pattern formation establishing, yeah? And then again, you get B minus C. And so on. Yeah, forever, literally forever. Isn't math great? I can just make things happen forever. Yeah. So this is an infinite series. It's a famous one in applied math. It's an infinite geometric series. And an infinite geometric series is thankfully easy to close, meaning there is a finite expression for it and we can find it. So the trick with infinite series of all kinds is you want to look for something to factor out so you can find the series in itself. So infinite series are often recursive. They're embedded in themselves somehow. So you peer at this thing. So this is how applied math works, right? You peer at the expression and figure out a strategy for factoring that reveals that recursive structure. So in this case, the first thing I'm going to do is I'm just going to factor the b minus c's out of everywhere. Wait, this is a v. Right, so b minus c, there's b minus c in every term. You see that? Yeah, it could be anything. And then we get 1 plus w squared plus w cubed forever. Yeah? Now, I'm going to look over here, and I'm going to take w out of everything that has a w in it. We have found the recursion. Yeah? Do you see that this is that? Yeah? Okay. So let's call this whole thing here, this long series, let's just call it capital A. I'm just going to give it a label. When I do algebra, I do this constantly, and I'm going to encourage you to try it out and see if it suits you in algebra 2. There's some big expression, and you're not going to do anything with it right now. But you've got work elsewhere in the equation. Just call it capital A. Stop writing a bunch of terms. It's just reduce the cognitive load on yourself. I do this constantly when I do algebra on papers. I chunk big things and I avoid prematurely expanding because usually that's a better strategy.
We call them sausages.
Is that sausages? This is sausage A. Yeah, exactly. This happens. Sometimes these expressions are just monstrous, right? And you know you can't do anything with them. I'm also a statistician, right? A Bayesian statistician, and some of you know in Bayes there's this denominator, this normalizing constant that is always some ugly expression that cannot, you can't do anything with it. That's capital Z. Always. It's just this normalizing expression. And physicists is the same thing, right? There's a bunch of models with this normalizing constant. You just call it Z and ignore it for the rest of your life because it's hopeless to do anything with it. Okay, so in this case, this is not hopeless, but we just want to chunk it. There's this expression, and we found it again inside of itself. So what does that mean? Well, we've got this relationship here. We now know that A equals 1 plus WA. I'm going to pause for dramatic effect. Yeah, you see this. So, right, this is all A. It's labeled there. And I found A inside of it. A is equal to 1 plus WA. You see it? It's got to be true. Ignore the B minus C for a moment. That's going to matter. That's the real payoff. But that scales the whole thing. But this is what matters. So now we just solve for A, right? That's all we got to do. So A minus WA equals 1. A 1 minus W equals 1. And A is 1 over 1 minus W. And so that means the payoff, all C paired with all C, is B minus C over 1 minus W. Yeah, because it's B minus C times A, right? Because this is all A up here. Isn't that fun? You have closed an infinite geometric series. Does it feel good? Yeah. And there's a bunch of geometric series that can be more complicated, but the strategy for closing them is the same. Sometimes these get elaborate, sometimes you have multiple continuation probabilities and they alternate or they do interesting things. You can still close these expressions because they're geometric. They nearly always close. End of the lecture today, I want to give you another example of this strategy. But we'll pause on that. Questions about this? Does it make sense? Yeah? So we have done some algebra, and I hope it feels good, but we've learned nothing. Because all this means is...
I think maybe there is, I don't know, because now it's smaller than it was if it was just one round. So I think
no.
B minus C
nope.
times 1, really? This is...
Nope, there's no error, and it's not smaller because W is a probability. So the denominator is smaller than 1. Yeah. So think of it this way. A, 1 over 1 minus W is a number bigger than 1.
Sure.
Yeah, this is a little bit mind-bending. So this expression, 1 over 1 minus W, is the expected number of times you'll interact. Right? And no pair is going to realize it because it's not an integer. It's an expectation. It's an average across pairs. But if W is a very large number, then A is very big. So if W is close to 1, this goes to infinity as W goes to 1, right? And we're not going to let it go that far. But that's exactly what happens. If W is 1, that means you always continue, and so the expected number of interactions is infinity. As it approaches 0, this approaches 1. Which is the previous game we analyzed last time. Does that make sense? And so yeah, so you can think about this as just, it's the payoff you get every time, B minus C, times the expected number of interactions. Yeah? Question?
So 1 minus W is basically the inverse probability that it means the probability that the relationship does not continue?
Yeah, 1 minus W is the chance the relationship ends. Yeah, each time. Yeah. Each time you interact, exactly, and if that happens, there's no more B's, right? You're all out. Is this good? I think it's good to pause here because a lot of stuff happened. All right, let me show you the other way to derive the same expression, and the way that I would normally do it, and I'm going to use this a little bit later towards the end today. You can just exploit the recursive nature directly. So remember, the payoff to all C paired with an all C, they get B minus C on the first time. There's a W chance the interaction continues. But now, if the interaction continues, since the W's is always the same, it doesn't change, the length of your relationship has no impact in this model on the probability your relationship continues. I'm going to say that again. The length of your relationship, how many times you've interacted so far in this model, has no impact on the chance your relationship continues. It's always W. It's a memoryless process. And since it's a memoryless process, we can just treat it like they're starting from the beginning again. Yeah? So the payoff that all C gets against all C is B minus C plus the chance they start again plus the payoff of all C, all C. So this is recursive, yeah? And does the intuition make sense? It's like you're starting over, yeah? It's like the first date. Every date is the first date for this organism, right? It's always the same. And we can solve this, and I'm not going to belabor it. I leave it as an exercise to the student to prove that you get exactly the same expression. But you can probably do the algebra with your eyeballs now that you've asked your younger sisters how to do it. Yeah. You get faster at the algebra, right? All of you used to be really good at it and you hated it, right? At algebra, and then you got interesting lives. And now the algebra's back, you're welcome. And but you recover it really fast and you get that rush from solving things, yeah?
I have a question.
Yes.
I don't understand why the V also appears again. Why can't we just let it at that?
It appears again because it's true. So it's a memoryless process. So every interaction is just like. So say, you know, if this organism existed in nature and we came across various pairs, there would be nothing about each pair that would tell us how long it had been together. And so if we were going to say what the future payoffs were in any particular pair, it would have nothing to do with how long they'd already been in a relationship. So each time they get to interact again, it's exactly like that state. It's like the first time. And so we're writing an expression for the whole sequence of their, what's the payoff across the relationship, but every interaction is like the start of the relationship. And so I'm using that intuition to write this expression. Yeah, it's like we go right back to a state. Yeah, you can think about this as the payoff of a state where we both intend to cooperate, is one way to think about that. But this strategy always intends to cooperate. And then we can solve it and we get the same answer. This is obviously easier than doing the whole geometric series, but it's nice to see behind the curtain and see what's actually implied. And sometimes this statistical distribution is interesting because sometimes the W's vary. Yeah, you can make models in which, this is the world's simplest repeat interaction model. You're welcome. But we can make the W's vary and do lots of things that are interesting about this. You can have partner switching. If I have time today, I'll talk about partner switching. Sometimes you just give up. Yeah, you don't just stop cooperating, but you try to find someone else to interact with instead of staying in this jail of a relationship. Sorry, too soon, too early in the morning for this talk, right? But you can make those models, and I have one to show you. Are we good with this? Okay. What do I want to do now? Right. What does all D get? I'm going to invent another. Wait, what do I call it? Do I call it all D? I'm just going to call it all D. Let's invent a strategy called all D, which is always not cooperate, always defect. D is for defect. Now I'm being judgmental, I apologize. Always not cooperate. They get 0 plus a W chance that they interact again. So they get 0 over 1 minus W. It's an even bigger 0. Yeah. They're essentially ignoring one another in this model. Yeah, they're in a pair, right? It's like housemates who don't talk. Yeah, something like that. So this is not going to change the evolutionary dynamics at all. We've added repeat interaction, but it's the same model. The same evolutionary dynamics because it's still, we've just scaled all the payoffs by 1 minus W because the strategies don't use the repeat interaction to do anything. So let's change that now. Let's introduce a famous, well, famous among game theorists. Among normal people, no, not at all. But famous among game theorists, a famous strategy in repeat interaction called tit for tat. Usually abbreviated TFT. And what does tit for tat do? Tit for tat is quote unquote nice. That's what people call it in the literature. Which means they start by cooperating. And then afterwards, every turn after that, if the interaction continues, you copy what your partner did last time. Just the most recent move. So this is the simplest sort of memory strategy. They remember what happened last time and they copy it. Yeah, not their own behavior, but their partner's behavior. So what is that going to look like? Well, against itself, if a TFT is paired with itself, it's going to look just like a cooperator, right? Because they're going to start out, we've got 2 TFTs and a bunch of turns. And they start out by cooperating. And then the next time, each of them looks at what the other individual did and copies it. So this C is mirrored there, and this C is mirrored there. Yeah, and so on, right, forever. As long as they keep interacting. And so the payoff of TFT paired with a TFT is just like the payoff of two all C's. Okay.
How is this different from Retaliator?
From what?
Retaliator?
Retaliator doesn't have repeat interaction, right? So it's responding instantaneously to the display or not, right? Whether it escalates or not. You can make, one of my first published papers, which is of no value, not even I cite it, no. One of my first published papers was a game theoretic analysis of repeat play in the Hawk Dove game with reputational dynamics. So individuals behave, they fight or not, they get reputations for that, then they meet new individuals who have access to that reputational information. So you can do lots of, I thought, fun, recursive, repeat interaction strategies in Hawk Dove, but they have different dynamics because of the fact that you've got this internal attractor in Hawk Dove changes a lot of things. Question?
So Retaliator with memory would be TFT then?
No. Let's leave Hawk Dove out of this because I think that's just gonna derail you. You want to just focus on this game. You're not going to get anything interesting from Retaliator because Retaliator Act doesn't have memory. And if he did, he would still behave as Retaliator, right? This is a whole different thing where the memory from last time is being used to choose what behavior they do this time. But I see the resemblance and why your mind's going there, but I'm going to discourage you from thinking of Hawk Dove right now. Does this make sense? Okay. We need to ask if this can be an ESS now against defectors, right? That's the first question you want to ask of a strategy usually is, could this be evolutionarily stable? It's common, they're doing great. This is sort of the best you can do in this game, yeah? But remember the problem with the prisoner's dilemma is that there's always an incentive to switch to not cooperating. An incentive. Natural selection, if it's got its way, would switch to not cooperating, yeah? So let's do that. And so we need to ask what all D gets. So we're going to imagine a rare all D in the population, a rare individual that never cooperates, and they're paired with a tit for tat. So now on the, and we can write it out this way, right? We can write our little game table. There are two individuals, an all D and a tit for tat. They interact on round one. And what happens? Tit for tat cooperates. All D non-cooperates. Yeah, right, in for not cooperate. That means that all D gets a benefit, right, on the first turn because the tit for tat helped it. Yeah, the tit for tat pays a cost, but we're not tracking the tit for tat's payoffs right now. We're tracking the all D's payoffs. And then there's a chance W, the interaction continues. If it continues to the second round, tit for tat copies the non-cooperation, and all D just keeps non-cooperating because it's an asocial strategy. It's just sitting there minding its own business. It doesn't understand why this tit for tat is angry at it, right? And that would continue forever because all D will never switch to cooperation, and so tit for tat is always going to be copying the non-cooperation from the previous move. Tit for tat's not clever, right? That's the point of this strategy and why we analyze it first is that it's sort of the simplest cognitive model of repeat interaction you can think of here. Just one memory. Are we good? Yeah? So it's W0. W squared 0, W cubed 0. It's all 0 after that. So it's just B.
Richard, what do you mean with one memory that you only remember the last?
Yeah. Yeah, you can make a bunch of strategies that remember more than once and then use the whole history that they remember to make choices. Those strategies don't tend to do much better though. Simple cognitive strategies do pretty well in these games. Yeah, I'm resisting the urge to go off on a lecture about that. I'm not going to, but there's a cool thing about how, yeah, cognitively limited strategies constrain the other strategies in interesting ways. It's like, living with a dumb person. There's just like, it makes you dumber. No, that's not exactly what the math says, but it's kind of like that, yeah? If nobody else is remembering stuff, it's not always advantageous for you to. That's one of the things the model says. Okay, so if for tit for tat to be an ESS, we require that the payoff to TFT against itself be greater than the payoff of all D against tit for tat. Yeah, that's the ESS condition for tit for tat. It means that a rare all D would not increase in frequency. So that's B minus C, 1 minus W greater than B. We can do something with this, right? I can make this B minus C greater than B minus WB. The B's cancel. We get WB greater than C. Yeah, your algebra is getting faster. I see some of you caught up to me. Or we can, so some of the art with this, this science is that you get these final expressions and you can arrange them in different ways, and you should feel free to play. Because the different arrangements, while mathematically identical, it's the fun of math, to your mind will look different, and you will learn different things from them. So WB greater than C means this is the condition for tit for tat to be an ESS, and what it says is, well, some function of the benefit of cooperation needs to exceed the cost. And you're like, well, I knew that. Right, that had to be true, right? But did you know it really? Now, now you know it. And that function of the benefit is a special one where the benefit is discounted by the probability of interacting again. Remember, W is a number less than 1. Yeah, I mean, it could be 1, but it's not. It's a number less than 1. So it reduces the benefit effectively in this condition. So say it's a half. Then half the benefit needs to exceed the cost. So this effectively means if the benefit is big enough relative to the probability of continuing the interactions, then tit for tat can be an ESS. What does this arise from? It arises from the fact that tit for tat gets to continue interacting. And so it gets to keep harvesting the B minus C's, which are positive, and that's good. But it gets exploited by rare defectors. So rare defectors will increase if the long-term benefits of cooperation, which is what tit for tat gets, are not greater than the short-term benefit of exploiting your partner. And that's all it is. The other way you can write this, you can write it purely in terms of W. W needs to be greater than the cost to benefit ratio. Yeah. So these are both now fractions. Yeah, so if say W is a half, that needs to be greater than the cost over the benefit. So if C were 1 and the benefit were 2, that would be exactly a half, and you'd be on an edge case. But you need something like, you need to make the B bigger, right? So like it's 1/3 or something like that. Does it feel different when I rearrange it? Yeah? Questions? Does this make sense? There are so many attentive eyes on the board, which is good, but that doesn't reassure me that I'm explaining things well. It could mean the opposite. Yeah. Is this good? This is cool. I mean, it's a very simple model. It's vestigial biology. There's lots of things to complain about here, but this is a new result. You've got this seemingly hopeless payoff matrix, but if we embed this game in a relationship and have contingent strategies of some kinds, those contingent strategies can, in principle, be evolutionarily stable against defection. So the repeat interaction transforms the prisoner's dilemma into something like a coordination game. You'll see this often in the literature. And these individuals that can coordinate on the better behavior can be stable against invaders.
So basically what you're saying is that for a rare non-cooperative to mute to tit for tats, you have to have this condition.
Yeah, so this is the condition for tit for tat to be an ESS. So the opposite, yeah, if we flip the inequality, we get the other. All right, for completion, let's draw up. Am I doing on time? I'm doing pretty good on time. Okay, let me finish up talking about this model. We're going to draw the triangle for this game. You know what the triangle is? Remember the triangle from last time? So this is really common in game theory, these triangle diagrams. And I showed you them before. So let's put this game on the horizontal right here. We've got all D, TFT, and I'm going to put a third strategy up there in a second. All right, so we'll have 3. But remember, this is the space, so this edge is the frequency of tit for tat. If you're in this corner, the population is all D. If you're in this corner, it's all tit for tat. What we've just shown is that if this condition is satisfied, then in the neighborhood of the world being tit for tat, selection can make it an ESS. A rare all D can't invade. What happens here? Let's ask the algebra. Right, so the payoff to all D against all D, what does all D get when it's common? It gets nothing. Nothing. It gets nothing forever. Yeah, it doesn't matter how long it keeps interacting, they're asocial. We've shown that before. The payoff to a rare tit for tat is, well, on the first turn, the tit for tat cooperates, because it's nice, is what they call it in the literature. I would prefer they used a different term that wasn't moralizing, right? We shouldn't be judging these, right? Sometimes these models are about fungus, and then it just seems weird to call fungus nice. It just bothers me somehow. As an anthropologist, I would like to reserve nice for talking about people, but yeah. So you cooperate, so you get minus C. You don't get any benefit though, because your partner doesn't cooperate. Then there's a chance you interact again, and then you get 0, and you interact 3 times, and you get 0, and so on. And so it's just minus C. Yeah. The relationship effectively ends after the first time in this model. But it doesn't end in the sense that you're still in the relationship in this model. That's what's weird about it. And so if I have time today, I want to show you a model where that's not true. You can actually leave and go searching for a new partner. Yeah. You can probably analyze this without any ado and realize that it is not looking good for tit for tat to invade. Yeah. Tit for tat does not invade when rare. We'll deal with that on Monday. Yeah. But so there will be some unstable equilibrium point in here, and you know how to find it. I'm not going to do it for you here. It's in the notes, but let me just motivate it for the sake of the lesson. Right? If we wanted to find this unstable equilibrium point that defines the basins of attraction for the 2 strategies, we would write the general fitness for each of these, and I'm going to do this so that you can remember, integrate the lessons from last time. Let P be the frequency of tit for tat in the population, and then in a population with only all D and tit for tat, the expected fitness of tit for tat is the probability it interacts with another tit for tat times the payoff it gets by interacting with another tit for tat. Remember this from last time and time before that? Or it interacts with an all D, in which case it gets minus C. And the payoff to all D in such a population, P of the time it gets B, which is the benefit of exploiting once, exactly once, the tit for tat individual. 1 minus P of the time, it gets 0. And then you set them equal to one another, and you solve for P. And I will leave that as an exercise to the student. This is in the notes, yeah? But the algebra will be, one of you has revealed that you experience euphoria when you solve algebra, so I will leave this to you. Yeah. Does that make sense, though? It's important to get the structure. The algebra, you're just going to get more comfortable with it, and that's fine. And I can't really teach you anything about algebra that you don't actually know in your body already, right? But it just has to emerge from you. But no, I'm available for algebra advice if you get stuck. Just let me know. But what's important is being able to construct these expressions and justify them. Right, that these are the expected fitnesses in a mixed population. And then we find the values of P which make these equal to one another, and that's the definition of an equilibrium. So in this case, there will be one of these unstable equilibriums. And if W is large, and this is what I explained, then it's really close to the all D point. So you don't need a lot of tit for tat. If relationships continue for a very long time, when tit for tat is rare, it will occasionally meet another tit for tat individual, but then relationships last a long time, and then it can invade. Yeah, but if relationships don't last a long time, or B is not very large, then it can be very internal, and then things look much more dismal. Good? All right, last thing I want to do with this before the top of the hour, we're going to add all cooperate on the top of this triangle. And we have to do this because the TFT world here, something interesting happens when you add all C. I think it's interesting, and it's really important to the evolutionary dynamics. Tit for tat is not evolutionarily stable against all C. I'm not going to draw that out unless you demand it, but just think it through. All C against itself gets B minus C over 1 minus W. Right? That's the benefit of continuing cooperation. So does tit for tat. They have the same fitness. And neither strategy is going to defect, is going to engage in non-cooperation. So they have the same fitness, and this entire edge is a bunch of equilibria. Good times. This happened before, remember? With Dove and Retaliator? Yeah, this happens a lot in game theoretic models. And my opinion is this happens because the models are very simple intentionally, and they leave out biological processes that make these strategies different. They leave out the cognitive costs, or very importantly, which I want to pivot to next, mistakes. I don't know about you, but when I have intentions and I try to do something, sometimes I fail. Yeah, and cooperation is one of those behaviors that can fail. Like, you really want to do it. You tried to help that person. You were going to take them to the airport, but you overslept. Yeah, that's a defection, but it isn't what you wanted to do, right? That's a mistake. The opposite mistake, not all mistakes are equally likely. The opposite mistake, your friend needs to go to the airport and you mistakenly pick them up at their house that morning, right, and take them to the airport. This is not likely, right? So some mistakes are more likely than others, but it depends upon how you define the cooperative behavior. And I think there's a point next in the next lecture where I bring this up again. This model of cooperation, we're thinking about cooperation as an action you do, but there are many cooperative behaviors which are withholding or stinting. We have this word in English called stinting. To stint is to not consume some resource you want, like dessert, right? You're stinting. People call it micro-fasting or whatever. People call this stuff now, right? There's lots of fashionable stuff on TikTok about this. But so in that case, cooperation is doing nothing, right? So think there's a lake with some fish in it. There's a limit that the community agrees upon how much fish you can take so that the fish population can replenish itself. Cooperation there is stinting, limiting your consumption of fish, right? Potentially not fishing at all. Defection means acting. And now the error calculus goes the other direction, right? Now the thing that is error prone is defection and not cooperation. So it does matter what story you tell. Anyway, I'm getting ahead of myself a little bit. So what happens here? Well, very similar to the Retaliator game in qualitatively, but not quantitatively. You want to imagine that there's some point along this line of equilibria where there's no longer enough TFT, and an invading all D will move the system in. Yeah. Just like, remember, an invading hawk when you had doves in Retaliator? That's the same kind of idea. So there's some point along here somewhere where we transition into this bad regime again, and all D can get invaded. Up here, there's enough TFT that the rare all D doesn't get to exploit, right? They're meeting TFTs too often, and the TFTs cut off the benefits. The ALD wants to meet an all cooperator. But if all cooperators are rare, then they have a harder time invading. Similarly, along this line, right, we've got all C versus all D. We know that all C is never an ESS against all D. All D is always against it. But there's going to be some place along here where TFT can invade, right, and actually do well. And in the notes, I talk about these dynamics more. This good? So yeah, I mean, when the TFT papers, the tit for tat papers first came out, they were presented like a tit for tat is a candidate for a strategy we should be looking for in animal societies, and I think that's a mistake. And the mistake is because look at this diagram, right? There's the problem with nice strategies like tit for tat is they can always be invaded by other nice strategies. And that those nice strategies may not do the police work, so to speak, that tit for tat does. And so it's the problem with Retaliator all over again. Retaliator is policing the community, but it doesn't police the police, right? Who watches The Watchmen? You guys know these?
This is the second order.
The second order, yes. Everything is second order, and third order, and fourth order, and yeah. Does that? I just want to bring forth that dilemma for you, that you solved one cooperation dilemma and you've created another, effectively. So there's a bunch of literature, really interesting literature, that takes off from this point, considers other strategies, variations on the game, what should we be predicting empirically, and beyond the idea that nice strategies do well in certain environments, it's hard to say exactly what the predictions are, unfortunately. But
that's because there's no benefit actually of self-help.
no, you can make public good versions of this and get the same problem. Okay. It doesn't, because it changes the private cost, basically. Yeah, if you add synergies, then I think it has a bigger effect. But I'm going to do something else now for the remainder of our time. And I want to talk about mistakes, because as soon as you start modeling, this is my opinion, but it's not only my opinion, is as soon as you start modeling repeat interaction, it is essential that you add mistakes to the model. Because otherwise, the model is often uninformative. You get these weird giant regions of neutrality among strategies that seem really different cognitively. That seems wrong. And there are many things you could do ad hoc to change that. You could just impose a cost on tit for tat for the cognitive machinery it's required for memory. Okay, so but that's not going to produce anything surprising. It'll just make it harder for it to be an ESS. It's a constant non-frequency dependent cost of having memory or something like that. Way more fun as a modeler is to introduce something that's endogenous to the system, that changes the internal dynamics, but is also realistic. And so the big thing in the literature is mistakes. And when I review new game theory models on repeat interaction, I always insist that there be an error analysis. I'm that reviewer. I like to think I'm constructive, but I justify it. I say we learned from the last 30 years of game theory that these models can't be understood in the absence of mistakes. That's what I would say. So I want to give you a glimpse into that today.
Mistakes is always for repeat interaction.
I'm going to define what I mean, and there's lots of different kinds of errors. So errors arise because the strategy has intentions, but sometimes the world gets in the way. You want to cooperate, but the action can fail. Or you want to not cooperate, which, remember, in the common pool resource version, not cooperating means going fishing. Sometimes you're a bad fisherman. Yeah, you tried to get some fish, but you failed. Your defection failed because you're a terrible fisherman. Yeah, could happen. Yeah, as opposed to, and cooperation can fail. I'm sure you can use your imagination to think of scenarios. That kind of mistake is called an implementation error. Implementation error. And that's only one kind of error you can make, because nature is nice to us. There are more. Yeah. The other main kind that's analyzed is called a perception error. And I'm not going to talk about perception errors a lot today because I don't have time, but Both of these errors are important, and they can both happen. Depends upon the system you're interested in. So the implementation error is a case where, say, you intend to cooperate, but you fail. Your partner doesn't know your intentions, right? All they know is the consequence. They know you didn't cooperate. That's the implementation error. A perception error is when you actually cooperated, but your partner thinks you didn't. Search your memories. This has happened to you. Yeah.
It's a wrong assessment.
So it's all about the perception of what happened. Yeah, not about what actually happened. Implementation errors change what happens. Perception errors change your perception of what happened. They affect memory. Yeah, they're like errors in memory, or they're errors in the sensory system. This is an error in you doing the thing you intended to do. They can both happen, and we can analyze them both. I'm going to start with implementation errors. The whole second half of the notes for this week is about modeling errors, and I give you a lot more detail than I'm going to be able to do in the time we have here. So how would we add an implementation error to this model? Let's make a new symbol, little x, or x, as we say around here. And little x is going to be the probability of no cooperates when an individual intends to cooperate. And there's no, I'm going, for the sake of simplicity, no error in the other direction. There's no case when you intend to not cooperate and you accidentally cooperate. You can do that. That's a great exercise for the student to add that to the model. I will give you all the tools necessary to solve that model. But I'm going to solve the simple one because I'm trying to teach you, not confuse you. Yeah. So we can use this to think about, in the simplest sense, just ESS conditions again. And then there's not a lot of new math. Well, famous last words. So let's just think about, for example, how this affects, what would be the easy thing? All D, think about an easy case, like all D paired with a tit for tat. What is the payoff it gets? Remember, on the first meeting, the tit for tat cooperates. Well, does it? It intends to cooperate. Now there's a chance it fails. So 1 minus x of the time, you get B. Remember, you're all D, so you get a benefit. Yeah. And x of the time, you get nothing. Then on the next turn, if you interact again, the tit for tat will simply copy your behavior, but you defected, so the tit for tat defects. There's no error in the other direction, and so you just not cooperate with one another forever. Yeah? And so this is 1 minus xb. So it's a little, it's less. Yeah? So this is the first effect of this, of mistakes, is it reduces the benefit of exploiting cooperative strategies because they're less cooperative by accident, yeah, depending upon X. It has much more fun effects on cooperative strategies with themselves. And then we start to see differences in this big neutral zone, right? The strategies start to act differently because the errors affect them differently. So let me think about how to do this. So we're going to think about two tit for tats interacting now, right? So
sorry.
Yes.
And something, because when the whole defector fails, wouldn't have a cost to that, maybe?
We're just doing this is the payoff to all D, so there's no cost that appears because it never cooperates.
But what it means, a mistake in this case.
The mistake means that tit for tat doesn't cooperate on the first move.
It's a mistake on the tit.
Yeah, exactly. Yeah, tit for tat makes the mistake. Aldi can't make a mistake because it never intends to cooperate. We're going to have more fun now, though, I promise. My definition of fun. I think we've got just enough time for this. In the notes, I show you all the algebra, but I want to get the concept down for you. So when you go look at the notes, and there's a whole box where I do the equations for you, but the setup is what matters, because the equations is just 3 simultaneous equations with 3 unknowns. And I know you all graduated from high school, and so you know how to solve that problem, right? 3 homogeneous equations, 3 unknowns. Oh yeah, go to work. Your younger sister will be really good at this. Yeah, but that's the whole box where I set it up. It's the setup that matters, though, because that's the translation of the biology into the math, and that's what I really want to teach you how to do. So we're going to think about, all right, let me motivate this and then show you a framework for translating it into expressions. I want to model tit for tat against itself, because I want to consider what errors do to its ability to be evolutionarily stable. Right? So this is one of the things we want to do. It's not as simple as this, because you want to think about a stream in the relationship. The 2 tit for tats are cooperating until one of them makes a mistake. And then that mistake will result in a non-cooperation act, which on the next interaction will be copied by its partner. Right? Its partner's very upset. Yeah? And then that will be copied by its partner, and so on, until someone else makes a mistake, and then they can both end up defecting. Yeah? Or, anyway, let me draw out all the possibilities. So we want to, this is a lot to keep in mind cognitively, how you're ever going to write an expression for this complicated stream of possible futures in the relationship. And the answer is, we're going to use a Markov chain. We're going to represent it as a Markov chain. And then maybe that sounds scary. Some of you were like, yes. and the rest of you were like, what? But I'm going to explain it graphically. Okay, so let's think about this system as having states. When you start a turn in this game, both individuals have intentions. And the state of the game are the pair of intentions of the 2 players. The intentions are to cooperate or not to cooperate. Yeah, and those intentions arise from the strategies. All C always intends to cooperate. All D always intends to not cooperate. Tit for tat, it depends upon what happened last time. Yeah, but we can write down those 4 states. There's CC, you, the focal individual, intend to cooperate. So does your partner. You intend to cooperate. Your partner does not. Your partner does not intend to cooperate, and you do. And neither one of you intends to cooperate. Bastards. Yeah. And now we're going to represent the transitions between these states using the symbols we've invented for the model. So you come into this node, you both have intentions to cooperate, but then different things can happen. The first thing that can happen, the best thing probably from your perspective, is that you get to come right back to this state, and that'll happen if neither one of you makes an error, right? Which happens with probability 1 minus x squared. That means both of you intended to cooperate and both of you cooperated, and that means, and then you get a payoff from cooperating, and then you're right back to the same intentional state, because you're going to copy one another's moves and you intend to cooperate again. Does that make sense? This is a bit weird, but once you get your head in it, this is the master plan for writing these complicated expressions. And you can deal with lots of stuff this way. Other things can happen. We could transition to this state. What's the probability that we transition here? 1 minus x times x. Why is that? Because you don't make a mistake. Wait, how's this work? One player makes a mistake and the other one doesn't. Which way does it have to be? Let's think it through. So if you intend to cooperate again, then you made the mistake, right? And the other one didn't, because the other one's going to copy your defection from last time. So this is, you make a mistake, the other player doesn't. And then you transition to this state. Yeah? Similarly, you could end up here if your opponent makes a mistake. Yeah, your partner makes a mistake and you don't. Then you transition here. Yeah, there's one thing left. You can add up, remember the law of total probability? So we can add up 1 minus x squared, x1 minus x, x1 minus x, and there's something missing. There's some probability mass left over. And what is it? It's x squared. Yeah? And so there's this chance that you go all the way down here, x squared at a time. You both simultaneously make errors, x squared at a time. And then then you both intend to defect again. Once you're down here, I'll do this since we're here, you're stuck here. There's a probability 1, you come right back, right? Because you don't have the opposite kind of error to get you out of this. So it's an absorbing state, the intention to defect. Yeah, because you'll just keep copying it over and over again. You with me, how this works? We're going to complete the diagram, and then the notes, I show you how to solve this whole thing. I'll do a little bit of it here. We get to this state. The chance that we end up in NN is the chance that the individual who intends to cooperate actually defects, so it's X. Yeah? And the other thing that can happen is you go over here, right, which is 1 minus x at a time. You don't make an error, but now you're just trading recriminations, right, because you're tit for tat and you keep copying the other. And so you can bounce back here as long as there's no error, you'll just keep bouncing back and forth in this loop. And this is awful. This is the problem with tit for tat and errors, is that it's stupid, right? And it seems like a really smart strategy in the absence of errors. But in the presence of errors, it has no way to repair the relationship, right? The only thing that you could either, as soon as the first error happens, it either you spend a really long time in this loop, or you end up getting no cooperation at all. Yeah, and that's what happens. Yeah, Christine, there's a question.
Yeah, it's really interesting, this example, because I find so, because you can have this assumption that actually you intend to cooperate, but don't do, and you also face the consequences of non-cooperation. But you know, there is this really famous as a strategy, the generous tit for tat, which actually is the reverse case, right? And there, the mistakes, or it's not mistakes, but the forgiveness of the non-cooperative act even makes cooperation more likely. Mm-hmm. So it's quite interesting because it's quite the opposite dynamic at the end.
Well, there's a lot to be said about that yeah, it's a good point. And there's other strategies that try to deal with this, and a famous one is generous tit for tat, which requires more defections, right, if I remember it correctly. And that helps with the errors, but it hurts with stability against invading bad strategies, because now defectors get to exploit you twice. The strategies that do well in the presence of errors, at least implementation errors, are ones that try to model the intentions of their opponents. So there's this thing called standing in the literature is what you'd look for, this literature on standing. In my first book, the one that no one reads, there's a bunch about standing strategies, and I analyze them for you. Standing is whether standing is like reputation, but it's something a single individual assigns to you, so it's personalized. It has to do with personal interaction. So the person views you in good standing because you cooperated with them. You're in bad standing when you defect with them. There are strategies that use standing to regulate when they cooperate because they want to be in good standing. So they will choose to cooperate sometimes just to get back into good standing with you. And that repairs this loop. Yeah, but it has other effects, right?
It's interesting, you can apply to different cultures. For example, if you have low trust cultures, so they may end up in this model much
yeah, sure.
maybe as a generous thing.
Maybe.
Judeo-Christian as well.
Yeah, I mean, people love to analyze their moral heuristics in these games, and I think the pattern, and that's interesting because you learn things from it. The pattern is that there's no master strategy in these games, because in any sufficiently repeated game, there will be some way for something to invade. That's just it's just complicated what happens. You can get these crazy. I mean, once people started analyzing repeat play, you can posit strategies, for example, that use the initial rounds of play as a secret password. right? So they play a sequence of cooperation and non-cooperation just as a private like door knock to one another to indicate that they're the same type, and then they cooperate if the password is completed. Those strategies are really stable. Like they can often do really well, and if interactions last long enough. Yeah.
You can do mistakes on that.
And then you add mistakes and everything goes to hell. Yeah, this is why I always insist, I'm that reviewer who's like, you gotta have mistakes in here, and here's the following reason, and I cite some papers about, I think, yeah, systematically, if you wanted to get the wrong idea about the evolution of cooperation, you would analyze these games without errors. That would be a great program, right? But we want to understand things, and so we want to model errors. And rare errors can have a big effect. X can be a small number, but as soon as it happens, the benefit of tit for tat is effectively halved over the duration of interactions, yeah, after the first mistake, because it's stuck in this feud, this completely dumb thing that you as a human observer are like, come on, sit down, let's have an intervention, like let's talk it out, right? But this isn't, you know, this is a general biological model, and we have to add all that stuff in. Does this make some sense? I have 10 minutes. So yeah, in the notes I show you, you can take this and write it as a system of equations, and then it's just solving for unknowns, and then you get payoff expressions that are over every possible dynamic in this Markov chain, right? So you think about any particular pair, if you simulated pairs interacting from this Markov chain, it would be like, let me try to animate it for you. Like we're gonna start here because they're tit for tat and they intend to cooperate, and they're gonna stick here for a little while because neither makes a mistake, right? So we're just going, right? This is my dynamic web graphics, right? And then someone makes a mistake, and we go here, and then we go here, and we stick here for a while, yeah? And then we transition down here. Every relationship eventually goes here, as long as if interactions continue. So we're also flipping the W coin every time to see if we interact again. That's also part of these expressions.
I want to ask a short question. Before you mentioned when you end up in this non-cooperative state, you mentioned is a state where you have the intention to defect, but actually it's not the intention to defect, it's just you intend still to cooperate, but end up in mutual defection, right?
If you go from like here to here, one individual you intend to defect, and it's the other individual makes a mistake, and now you're in mutual defection. Yeah, and the opposite here, you intend to cooperate, but you make a mistake, but you end up in the same.
Okay, and it's also the intention.
Yeah. These are states. All the states in this Markov chain are intentions. Your behavior arises dynamically from the mistake probability. Yeah. Does this make some sense?
Yeah.
Yeah.
Yeah. It doesn't matter if your intentions, the consequences count.
Exactly. And so the conceptual insight I want you to get from this diagram and the solution strategy is we want the average starting here of all the possible trajectories a pair could take through this system. And if you simulated any particular system, you wouldn't get the average. You get some particular payoff because the relationship would last some finite number of rounds, and there would be some particular history of mistakes. And it's that total joint probability distribution of the mistakes and the length of the relationship that we have to take an average over. And that sounds horrible, and yet it's trivial if you know how to use the Markov chain. And that's what I show you in the notes. We're going to write expressions exactly like the ones we did before for tit for tat with the W's everywhere. And there's just going to be 3 unknowns now instead of 1. So we've got an infinite geometric series, and it's got 3 unknowns, and that sounds horrible. What are you saying, Richard? But it works exactly the same as the simple examples. You just have to solve for 3 things now instead of 1. And again, your younger sister is very good at this. And yeah. But the intuition about how to do it is what matters. So we're writing the probability, the payoff that happens when you enter this, and then the probability you transition to a particular place, and we can write it out as expressions with terms for each of the events, and then we just do algebra, and you get a closed expression. And what happens, since I'm running out of time here, what happens is, unsurprisingly, probably to you, mistakes hurt tit for tat, right? So how much does it reduce the payoffs? After you write this down as a system of 3 equations, and you solve for the payoff of tit for tat versus tit for tat, which means for a pair starting in this state. That's what we do. And it is, what is it? Yeah, 1 minus x, wait, yeah, 1 minus x b minus c over 1 minus w, 1 minus x. Sorry, my handwriting is terrible. Yeah, so first thing you want to do, imagine you've just done 2 pages of algebra to prove this thing your instructor told you was true. Yeah, and you've got the right answer. You've checked it against the instructor's solutions. You're feeling great. The next thing you should do is think about taking the symbols in this result and putting them at extreme values to understand how the expression behaves. So if we increase x or decrease x, what happens? So if x were 0, this becomes b minus c over 1 minus w, which is the previous model without mistakes. That's good. That's a good sign. That doesn't mean you did the algebra right, but that's a requirement that the algebra is right, so that you get the old model back. Yeah, you could have it could still be wrong, sorry, it's true. It's not a guarantee that that tells you did it all right. As x increases, it reduces this payoff, yeah? It effectively reduces the length that relationships last. Why does it do that? Because you get sucked into the vortex down here eventually, right? And then the relationship effectively ends. And it reduces the rate at which you get B's in the long run. Yeah, so that's the intuition you get out of it. Does it make sense? And I show you also in the notes and the examples that this changes the evolutionary stability of tit for tat versus the other strategies. It can be stable against one or other of all D or all C, but not both. And that's because all C repairs its relationships. In the face of errors, all C does great with cooperative strategies because it never gets into a feud. So all C paired with TFT does better than TFT paired with TFT. And that affects the evolutionary dynamics of the game. Isn't that cool? I think that's cool. Yeah. The dumb strategy has an advantage in certain populations with certain error structures. I am out of time. I wanted to talk about partner choice as well, and I don't have time to derive the model for you, but in the notes I've got this full partner choice model in which the lifespan, we've got this symbol L, which is the lifespan of the focal individual, and we divide their life into a series of relationships of different length, and each of these relationships has inside of it some length of the relationship, capital R, and then you choose to leave it and you spend time searching, and that's capital S. And sometimes the relationship is long and the search is small. Sometimes the relationship is short and the search is long, and so on. These periods vary, but they have an average. They have a statistical distribution. And I show you in the notes, and this is the same math you use to solve the basic game. It's not complicated at all. That in this version of a model where you can, when you get we introduce a strategy like tit for tat that leaves the relationship when its partner defects on it. And then it has to spend some time searching. So there's a search cost. Yeah. And then it can find a new partner and it can try again. So sometimes these relationships end after the first round because it met a defector. Sometimes they continue for a while until the W happens to you and the relationship ends. And what I show you with this model is that it's very bad for cooperators. And the reason it's very bad for the cooperators is that there's a big ocean of defectors out there that are free because no one sticks with them. And so when you go searching, that's who you find. It's like online dating. No, too soon, right? But yeah, but so this model of partner choice, there are other models of partner choice, but this one makes things worse. It makes things manifestly worse because from a population of cooperative strategies, you're polluting the social environment when you let the defector loose on other people, right? And there's just a desperado going town to town, scamming poor widows, right? Or whatever movie trope that you want there. There are other partner choice models that have more promising results, but it's important to do each mechanism of partner choice and think it through carefully, because most people's intuition with this model is it's going to help you, right, if you can move on. But it doesn't with these minimal assumptions. That's not a claim that there's no model where partner choice is beneficial. Okay, it is exactly 10:30. I thank you for your attention. Homework problem is up. I don't think it's too hard, and I think it's interesting. I'm going to ask you to reanalyze the more basic tit-for-tat model. On Monday, when we meet again, I'm going to look at another mechanism for encouraging cooperation, and it's one we can blend with repeat play, and that is inclusive fitness or kinship. When you interact with your relatives, your genealogical relatives, what does that do to the dynamics of a game like this? Okay, thank you very much, and I'll see you next week.